Okay, so I want to introduce Emil, who is from, just finished his PhD at Chalmers University in Gothenburg in Sweden. This is his PhD. It is online. You can download it. You just Google Emil's name and Geometry Linking the Art of Building in the Universe, and you can get a copy of his PhD, which describes his work on looking at grid shell design and also running workshops on grid shell design, such as the one we're doing. And Emil's an old hand at this and has been doing this for a while at Chalmers. He's got a great pedigree. I really recommend you read the book. The PhD, it's a very readable PhD, unlike most PhDs. Emil's has got some lovely bits at the start, certainly, that you can just sort of read about shell design and so forth. And he's got a great pedigree. His supervisor was Chris Williams of the sort of British Museum Great Court Roof fame, who also worked with Chris worked with Ian Liddell, of course, who we all met yesterday. So it's almost like Emil is the grandson of Ian Liddell in a certain sort of intellectual sense. So we've got a nice lineage going on here. So I'll probably just give the floor over to Emil. Emil, how do you want to do it? Do you want them, are you happy to take questions midway through if people want to stop you, or would you rather we just wait to the end? Or
it's depending a bit on the time here. There's quite a lot of material, so maybe in that regard it would be better to take the questions afterwards, in a sense. So, but otherwise, I have no problem with taking questions in the meantime, I think.
Okay. All right. Okay. Well, we'll see how we go. We'll see how we go. So
Yeah.
I'll hand it over to you. I've made you co-host, so feel free to share your screen, and off we could go.
Yeah. See, so it comes to right one here. So share screen one, I think. See what happens if I press the.
We can see your architectural geometry, Emil Adiel.
Yeah.
Yes, that's all there.
Do you see the full screen and not the presenter view? So you see.
We don't see presenter view. We just see the presentation.
Okay.
Yes.
That's great. That's great. Thank you so much, Allan, for the presentation. But actually, I'm not the finished PhD. So here in Sweden, we have something that's called a licentiate degree. So I actually have a couple of years left on my PhD, actually. So the PhD is 5 years usually in Sweden compared to, I think it's mainly like usually 3 years in England, maybe, or UK. Oh yeah. So actually I have some stuff to do left, but I think it's rather fun. So hopefully the thesis will be even better next time. This lecture, so Allan asked me to do this. So, and it's mainly about architectural geometry, but also the workshops we have been doing here at Chalmers, since it could be interesting for you for your projects. But I will also talk a bit about differential geometry, since it's linked to that, how we run our workshops. And if there's time, there will also be a bit on the theoretical research we are doing at the moment. So some part of the architecture and engineering research group here at Chalmers, and it's a group consisting of both architects, engineers, and also Peter, who is actually an artist. So it's really this mixed group of knowledge and cultures, in a sense. And as Allan said, Chris Williams is my main supervisor, and also I have Mats Ander and Claes Mondin, who is my co-supervisors. Geometry is something that is a very big part of our group. So we've been host of Smart Geometry in 2016, and also the Advances in Architectural Geometry, AAG, in 2018. And as you probably know at this stage, maybe you talked about all these projects, but Chris Williams have worked with IIA, for instance, on the Mannheim Multihalle for a couple of years ago, and also known for the British Museum Court Roof. So there's a lot about the connection between geometry and structural behavior and so on. So But the reason I started to become interested in this was I did this internship at the Bureau Happold between my bachelor and my master's, and in the Smart Solutions group at that time. So we worked a lot with geometry and these kind of projects like the Singapore Jewel. So it was form optimization and also about fabrication or production, and developing these little tools like these node clustering, for instance, together with other people like Isaac and Emma Paulson, which you will see more in the workshops later. So there I kind of became interested in this connection between, because that we had to solve some issues, and I realized there was some connection between the form and the patterns and the forces, but I really didn't get everything at that time, and I'm still trying to learn all that. But I think it was through these kind of projects I became sort of interesting to continue with that when I came back to Chalmers for my master's. So I think that was kind of an important period or year. But the main thing I'm going to talk about is, these kind of workshops, usually workshops, what I mean by that in this sense, because it can be many meanings, is when you have a certain amount of time when you meet and you have some sort of objective and you do that, and trying to combine both the digital modeling and building things, smaller or bigger models, so to say. And I thought, so I'm going to focus a bit on that later on, kind of design process we have been doing, because I don't know how much, I'm not an expert in sort of design process, but maybe it's showing how we've been doing it can be interesting to you. But really, so what's really the connection between geometry and the workshop? Actually, I think, it's very difficult, but many do believe, and I can also believe that geometry comes from the crafts. So if you think about it's for a weaver or bricklayer, the form and pattern is very much related for structural reasons, and that was probably more evident for the craftsmen and craftswomen before we could actually have the math to describe that, or the theory, obviously, because that's only like 300-400 years ago we started to talk about the kind of theory we have today. So there's a great connection there. And also when we talk about this kind of workshops, it's about the sort of head and hands relationship, which has been very important. So reading books, I can really recommend this book, The Hand by Frank Wilson, who's I think he's a neurologist. So, and really tries to describe this marriage between the head and the hand, how it's actually very, very important for our learning historically, and how we actually are biologically trained to actually work both with the hand and the head. And there are different types of books I can recommend you if you want to read more about this kind of the craftsmanship, and also a bit about the workshops, like Richard Sennett's, describing how this kind of, basically, we have been learning in the workshop, not least learning by each other and so on. And all these books could be interesting to actually understand. And the second book there, the Together, is maybe even more important today when we sit so much isolated at home and so on. And all about this craftsmanship and so on is also related to this about the Davos Declaration. I don't know, not many people have heard about it, but it's basically some declaration signed by the EU Ministers of Culture, trying to get some documents, trying to define sustainable building culture, where they really focus on the process and this holistic view on the design and design process and the effects. and also emphasizing craftsmanship, and not that it should be conservative, but it's the connection between local, knowledge and new digital tools and all that. So that is also something that is quite related to this, I think, stuff we do. And also focus on the historical structures and their importance for the future. All right, but I will jump into a bit more theory now in differential geometry, which will be important for the talking about the workshops later. So differential geometry is basically language for describing curved geometries, at least the way I use it. And you can basically say it's about, I use it as describing, space curves. It could be describing surfaces, and then also curves on surfaces. Space curves, you get these coordinate system where you have the tangent you probably know, but also the curve normal, and also the binormal. And you can use this to actually describe the different properties of the curve, the curvature, which is the kappa, and the torsion, which is tau. And that's really useful to when you actually talk about it and try to understand the properties of these curves. And the same thing can be done for surfaces. It gets a bit more complicated when you're working with surfaces, obviously. But the difficult thing with working on these curved surfaces is that the base vectors, your coordinate system continuously change. So that's the A1 and A2, which is in the plane of the surface, and the A3 is normal. But we can use this to also describe the sort of properties of these surfaces. So the metric tensor describes the lengths and the sort of angles in this grid that you see. And the B, alpha, beta are the components of the sort of normal curvature tensor, which is how much these bends in relation to the normal to the surface. And you can basically use this then to describe this pattern very much. And you can think about it would be good to, they can decide this however you want, but you can't really, unfortunately, because you have the Gauss-Codas equations, which is 3 equations, which describes, it's basically, in a sense, like compatibility equation, I think, sort of making everything, how the A and the B's actually fit together, so it actually becomes a surface in the end. And the first one, the Gauss equation, is basically, so describing if you would actually walk on a surface. So it's describing the intrinsic property of a, so basically if you lived on this surface, you could actually know that you live on a curved surface, which is basically pretty without seeing it. So if you basically would point in a direction and walk with this vector in the same direction, and then come back at the same point, you basically have an angle, and then you basically would know that you live on the curved surface without actually seeing it. And the last one, the B alpha 1, and the covariant derivative is the Codas equations, which also has to do that everything fits together. So that's kind of decides, these are sort of the main equations that you need to at least know about working with these kind of things. But what is really then, you probably heard about the Gaussian curvature, and there's a very, when I started learning this, it's many different types of curvatures, but the Gaussian curvature is a measure of surface curvature. And we can describe different properties in the sense of if it's positive, then it's due to that you have 2 positive principal curvatures, you could say. That's the K1 and K2, and I will come to that. But you can also describe it as you see with the B11 and B alpha beta and A alpha beta. That's the way how they kind of connect. And if you have negative, then you have the principal curvature in two different directions. And if it's 0, it doesn't mean that it's kind of flat, as a cylinder has 0 Gaussian curvature. What it means is that you can actually, flat it out to become a flat plane. So you can always cut the cylinder and make it a flat piece of paper, but you can't really do that. And the more Gaussian curvature, the more difficult it would be to build something. Usually if you have a gridding problem, that's you want to have a low Gaussian curvature in a sense. But if you're, for structural reasons, it could be really good to have more curvature. So, and the principal curvatures are the maximum curvature in the normal direction. So if you think about the normal and how much each of these curves, so that's the direction you would know. So it's in a sense related to the principal stresses in a sense, but it only has to do with the normal. So when we have curves on surfaces, we can always relate them to the surface normal. And if we use these mean curvature, if you add them together, divided by 2, we get the mean curvature. And if you have 0 mean curvature, then it's a minimal surface. So why is all this good to know? So we can use maybe an example. If you see this anapurse surface, it has this description. And if we use all these equations that we saw previously, we can actually calculate the A1s and the A22, A12, and the Bs. And you could see then that you can, for instance, see that you have 0 mean curvature. You can also see that the B12 is 0 and the A12 is 0. So basically what you know then is that you have principal curvature parameterization. It's a minimal surface, so you basically know that all these angles are at 90 degrees, and you also know that you have flat panels everywhere. So it could be sort of good to to know then about a way to describe these surfaces. But then we also have the curves on surfaces, and similar to the principal curvature directions, we sort of relate its curvature to the surface. So, this equations I showed previously about the curvature, when we have it on the surface, we can actually divide it into what is called the normal curvature and the geodesic curvature. So the geodesic curvature is when it bends in the surface plane, and the normal is only if you project the curvature vector onto the normal, basically, and see how much the component there. And if you have 0 geodesic curvature, then you would have a geodesic. And that's a special type of curve that's only bends then in relation to the normal. And it's also locally, at least, the shortest distance between 2 points. So you can kind of see it in both ways with that. So it's a shorter distance locally, but if you have the other one where you only say it has to bend in the normal direction, you can see that it can take this quite strange way on the torus. And you can get back at the same point, but it's not really the fastest way in a sense. Right. And that leads into the first workshop then, which is this Geodesic gridshell one, which we built in 2017 with our students. And it was together with people from Birhapple, Core Studios, and Big Engineering. You can see all the names of all involved there. And to get a bit of a context about this, why we did it and all the things around it. It was part of a course actually, which is only 8.5-day course with our second year architecture and engineering students. where they get to learn about parametric modeling and digital fabrication, and they do a bit of, assignments and small projects, and they build, this little, not this one potentially, but, models you can build on, on your desk and stuff like that. And that's all fine, but we kind of wonder, we talked about, what happens when you get a bigger project. You can't really, build it on your desk. You have to think about all these things about what happens if you have to, divide all the pieces, the erection process, the production process, and so on. So we thought that why don't we have a workshop to sort of summarize, because we managed to fit all the requirements in those 6 days, so really packed it. And so we basically had 2.5 days to do something fun, and we're a bit free. So we thought about, we know that we want to do a space, it's in December, so we don't do it outdoors. So we want to do an indoor pavilion of some sort. And it's going to be a space for this Christmas holiday ending, where they have a book release and so on. So we thought about what kind of things would we like to incorporate and what we need to think about. So we would like to relate it back to the course, the kind of stuff we've been doing in programming, some nice design, because they also study architecture and so on. But mainly was, we have to produce everything in just 2 days with our students, from scratch, from boards coming in basically to having some sort of structure. And we don't have a great economy. We only have, we could basically get, this amount of plywood boards and screws and so on. And we only have a limited amount of tools and so on. So we kind of, if you cut them in straight flats, that's the most economical way. So what can we really do with that? So we have to make it simple in a sense. We had a very simple, we had these limitations, but I had to make something exciting, And the sort of the methodology that we used was to think about different geometrical concepts and then go into this design process where we as a team try to, think about this kind of things, the form, the space, the limitations, the manufacturing process, analysis, and so on. And then go into this stage of producing everything, and then we do the experiments with our students. And so this is the couple of people who have been involved. So it's not only me that has been doing this. So it's me and Isaac Neslund, who was the teachers. I'm the course responsible, but Isaac was also a teacher. But it's basically a design team, has been different years, but so we do the design, and we try to actually package it so the students should be able to understand what we're doing. So it's not only that we do something that they don't really understand. So try to also make it into some sort of theory and application, and so they can learn from it. And so we have been, the first year was inspired by different projects like this Geodesic gridshell one, and we had worked a bit with Geodesics on this paper we did. So we knew a bit about that. So that's why we thought it would be good. And so going back to these Geodesic was talked about, there are different ways to sort of think about it. As I said, you can think about it as having 2 fixed points, and you find the closest point between them. So you can imagine that you have like a rubber band that you try to, or a core that is tightened between these 2 points, then you would get the closest distance. Or you can think about having a piece of tape or ribbon that you start in one starting point and direction, then you basically see where this goes. So that is thinking about it as having 0 geodesic curvature in a sense. But then we also, every time we have like a theory or something like that, we test it out. You probably learned Rhino now or something like that. Just implement it, some sort of script, then just check. So yeah, that looks pretty straight. That seems to be working. That's good. Let's go with this. And then it's also about understanding the limitations of your how much can we bend this? How much can we twist it? How we're going to do the connections, and so on. So basically starting to just building random stuff, and you check, oh, this tight, we can do it. So we know that. And then we, went into see what kind of shapes, because it's going to be a space, right? So we did some options, but we found out that it didn't really work because we didn't know how to design it, build it in a sense. It wouldn't really, because we're only working with sort of mathematical surfaces now. It's not actually, so you have to always think about that. It's going to be a real structure, some things will happen. And we actually realized symmetry would be real nice. And we had this floor where we're going to build it with a 1 by 1 meter grid. So we just took the base kind of curve, and we tried to match it at these and found the surface that's worked that way. And the good thing about geodesics, as you know, since you can decide how the pattern is going to be, depending on the sort of starting point and direction, we tried to find something that would look interesting, but still with very much, symmetry. So I think every element here is repeated 8 times. So it helps to speed up the process a lot during the, when we have the workshop. And we could also think about this kind of erection sequence in the meantime, sort of what kind of things should we start with? They can start from 4 different points and come to the middle. And, we really try to imagine the workshop, before in your computer before you're there. And we did everything in Grasshopper. It's not very pretty here, I'm sorry. It's an old picture, but just to show that we did everything so that the students would get the script and they could basically build it themselves and go into all the things we've been doing as teachers in the design process. And a lot of it is just, fabrication drawings and geometry checks. So we could basically tell the students, in your small, projects, you could basically stop at, the design of the grid shell, the geodesics, but everything else is used for checking, doing all the fabrication drawings. And this kind of, the way we did it was that we first, did this geometrical model, and then we unrolled all the lats and did all the holes and all the cutting and divide them up, and then build it up again. And the advantage was that you could check these kind of things. So since everything came from every lat has its own bolts, we could see that if they didn't match, there was something wrong. So we could basically use it as a way to check beforehand that everything would fit together. And these were all the drawings that we did. It's all the left are all for the lats, since we had to repeat it 8 times. And that's for the boundary. We only needed 1 CNC to run it, which saved time. And we were very confident from the, when we did the bending test, that everything would kind of work. We have this we can bend it very much, but Emil Paulsen did actually a bit of a quick analysis before because we kind of stressed at this point as well, because we don't maybe have like 1 week to prepare this. So something we're like, yeah, it's fine, but we actually realized we overutilized a bit. But we kind of thought, we'll be fine. It's not that big of curvature. But we will see if it's something, we might regret this. And now you will see the workshop, how from these 2 days. So this is Isaac showing the student the scripts. And now they cut up the boards, they come a 6mm plywood, and these are the paper templates that we printed out, and they had to, so we're using, we have, didn't mention it, but we have like 40 students So the fastest way was actually using all these simple tools. We could have done it with the CNC, obviously, but we wouldn't have time. But we made the base plates there, like you see here. And marking is good. Yeah, and you can kind of see it's kind of this teamwork, getting and a lot of dancing and stuff like that. They had the music on during the day, and that's also one thing that is important, to have fun during these workshops. Then it was assembly time. So we actually, we pre-drilled all the holes, and we're a bit stupid because we actually had the exact diameter of the drill and the bolts, so we didn't have any like tolerance, which was just stupid. But I had to apply some force sometimes to get it together. And here you can see the sort of teamwork, more dancing. Time lapse. So I don't think, I think it's really important to, see that they're having fun. We're a bit skeptical. We were a bit afraid that they would find it really boring, that we had done much in advance, but everyone actually got us different assignments. So we actually didn't tell them how to do things. So actually, divided them up themselves and so on. So we gave them the freedom to solve the issues themselves from the drawings and so on. So it actually became I think it was a collective ownership in the end, which was our intention. It was not our thing, it was everyone who was involved. And we also got a bit of breakage at one point, where, since I think we had a knot at one place and so on, but overall, I think it looked really nice. So I think we managed to get it to look quite natural. So like the result in the end. And the details worked pretty nice. But then we were in the same situation the year after and the year after that. So this is 2019, and we were still sort of what to do. Do you want to do the same thing? That's a bit boring. So I'm going to talk about this asymptotic gridshell instead. And the inspiration came from Eike Schling and Jonas Sikor, who did this pavilion. And we also did a previous one in 2018, which for some reasons you will see had some issues. And there's a bit of difference and some sort of relation between the asymptotics and the geodesics. So the asymptotics, it comes from, I think the name comes from, it's two curves that doesn't really meet. So I think you have this in, remember from math. But the thing is that you can sort of see the asymptotes that if you took a plane and intersect the surface, you would get these blue lines and they wouldn't really meet. But if you get closer and closer to the, trying to touch it with a smaller part, you would get this orange, which is almost touching, but not really. And then that's the sort of an approximation of the asymptotic directions. And the difference from that and the geodesic is that then you have zero normal curvature instead. So it only bends in the surface plane. And you, the B11 and B22 are zero then instead. And you can sort of think about using the Mohr circle of curvature, which is kind of the same as the Mohr circle of stress, where you can see how these principal directions are related to these asymptotic directions. So you can basically see that you have to have a surface which has both positive and negative. So it actually has negative Gaussian curvature. And if you have a minimal surface, this direction will be at 45 degrees against the principal curvature net. So that's pretty useful to know. And if you extrude these curves in the normal direction, you will get kind of an approximation of something that could be unrolled straight, like the geodesics. It's not exactly true, but we did build a dot model to test it out, and it was basically good enough for us. So it became, so that's kind of the idea usually, that we find a theory, implement it digitally, and we build a model to check it out. And the idea for the sort of shape was related to the erection procedure, similar to the Mannheim one, trying to see if we can find a shape where we can build it flat and just push it. And we tried to find ways to simulate it. It actually didn't become as accurate as the physical model. So we basically relied on this physical model to sort of understand, to see if it would work in the big scale. And the good thing of utilizing mechanism is good in the erection procedure, but as we saw, we know about this issue basically, but we didn't have any time to solve it, was that you have to obviously lock the mechanism when you're in the, when you have erected it. But we didn't really find the time to develop, with the tools we had, and a way to solve that kind of any bracing. But we had different models to sort of test the overall stability. But this is basically me and Isaac. He's standing on this ladder and trying to simulate this modal analysis basically. So, and I'm taking the important job as the cameraman, of course. So we tried to develop a new detail, where you can actually lock. So we actually had double layer, which we could then lock with this lock. But it also caused obviously some problems for us, because then it needs to basically slide against each other from, when you have flats, as you probably talked about them in the Mannheim. Yes, and when it's flat, you also get this, it's not really 90 degrees anymore because it's flat. So it's all these kind of issues. So we had to find some sort of way to produce it very fast, because we needed to have some sort of slots in the middle. So we talked with the people here in the wood workshop to sort of help us out. And they, maybe you can use this tool. So it's, and then can build this sort of workstation. And then we're pretty confident. We can probably build these in one day's time. But then we had to see if it actually, worked. So just building a little model, me and Isaac, to see if it's, because it's kind of difficult to understand if, the kinematics and stuff, for me at least. So, and try to model it accurately. So it's, spend a couple of hours just trying to see if the thing works. And now it's just, locking it and try to, So at this stage, we're kind of, I think this will work. So we're happy. But the thing was, it was a bit difficult, when you, so maybe we'll stumble upon the same thing in your projects. So I just mentioned some things. So when we flattened it, we had to think about, how this, that these will need to move and slide, and we need to calculate the lengths of how much, since we need to know the slots, the length of these slots and how much it will move. But the problem sometimes is, when we flattened it, it wasn't, we had to understand the difference between the flat one and how that bent and how it would bend on the surface. And depending on that difference, we will need to know if we would actually, because sometimes it would look very strange, but intuitively, but that would be the right way when then it would push up and so on. And, going back to just do some calculations here, Isaac did to find the difference between the angle, and it's usually for us, it's easiest to just try it out also digitally. So it's like, okay, now it works, then we can implement it on our structure. But then we also would need to think about, would it be a diff problem if, when you squeeze it, would these bolts that we built, will they also need extra tolerance and so on? So then it's really good to use your digital tools to see if that would be a problem, because that's really hard to think about. But we use the Rhino grasshopper to see that it would wouldn't need any extra tolerance for that. So, and then you just do some adjustments. But what I found, that's usually, you think about it as just some small adjustments, but you usually have problems with the boundary conditions, getting the right distance. Can someone put the screw here? Can we actually fit that when we push it together and so on? And these are the sort of drawings that we had for the students. The left ones are for at the boundary, so that you would use, sometimes you talk about high-tech stuff like digital fabrication, but now it just becomes, we have these different angles on the saw. How will we communicate that? In a sense, you can tilt it, you can rotate it. So I think more of it as trying to understand how to communicate either with a computer or a person doing it, in a sense. And you just have to be creative and think about, it's all about communication in a sense. And the one to the right is for the slots and what kind of machine they would need to use with different slots width and so on. And then also thinking about how the assembly would go and make different drawings. How would we know what direction to start with? Because now we have to think about also that they need to be in the right direction and different layers. And it was actually pretty difficult to get your head around that. So that could be good to think about. But now for maybe the fun part. See how it went with the erection procedure. This is from the workshop. So they're here in the concrete hole. See they're doing some, doing some building, some just having fun. And here you can see they build it flat. So this is the second day where they've been, so we started from just regular on the shelf stuff, 6mm plywood, 45 by 45, regular timber, and you can see the erection. And now they start to lock it into place. And then we had to do some adjustments because some students just, locked it before, thinking about, in a sense, you would need to have some better strategy to understand which one to, do first and so on. But you always think about that, and there's 30 students just, wants to start doing things. So, but I think it's became pretty good. And when we disassembled it, it actually just became this you know, we fitted all the lats onto two sort of these two. So that was pretty nice. All right, see, I thought I would talk a bit about some of the theoretical research. I don't know if I actually have some time for that, Allan, but maybe I can do it quickly.
Yeah, that'd be great, Emil. Yeah, just quickly,
Okay.
just show
Yeah, great.
nice link.
Yeah, right. So I thought I could talk about three different things here, but maybe I just, so this is more practical stuff we showed, but we'll also do some more theoretical stuff. And sort of the methodology we'll use is usually, you know, look in history, going back to the Baukultur, the Davos Declaration, and see historical structures and link it to some sort of math, and then do some development and see architectural applications, and then do some simulations. And one paper we did some time ago was on brick, see if we could find a way to describe brick patterns. And so we basically looked at old drawings and saw that they only usually describe the bed joints. So is there any coordinate system on a surface that we could build, that we can apply like that? So yeah, and yeah, also, sorry, it came a bit. So that was one thing we thought about. Then also see if we can link it also to the membrane theory. And you actually can, so you remember you had the lengths and the angles, the A, alpha, beta, and then you had the normal curvature and linearity, the B's. And then you also have the normal and shear stresses from the general theory. So you can basically combine these three, but then you have to think about, you have three equations for the membrane shell, and then you have three equations from the Gauss-Geodesic. And so we basically combined that into two different techniques. One that was only looking at the geodesic coordinate system, which has these kind of properties, and we used to do the grading technique, I call it, where you can apply different types of patterns, which is more geometrical, and then form finding where you generate the form and the pattern simultaneously due to these, since we know about the membrane theory connection. And then something we've done, right, is also looking at something that's called a special type surface, which all the points on the surface actually have what's called constant solid angle. And I probably don't have very much time to this, but basically if you took a curve and you correct it onto a unit sphere, you get this image, an area. And imagine you have a point cloud and you have a bunch of points, and all of these points will have the same constant solid angle. And so we use this Gauss-Bonnet theorem and also the Biot-Savart law to basically the Gauss-Bonnet to calculate solid angle, and the Biot-Savart law to understand what direction to move our points. And the good thing about that is that you can get the same sort of slope around the boundary. And that is usually a problem when you're working with, you know, patterns, it's the boundary. So then you could potentially, or you could make a principal curvature net since the slope is the same around. And we also looked at a bit on masonry bridges to basically see if we could, you know, reintroduce the these masonry bridges, because in UK you have a lot of masonry bridges that are still used even after a long time. So it's basically, if we try to find a way to see if we can use, because a lot of part of a masonry bridge is actually soil. So it's basically like a container in a sense for the soil. So we thought that see if we can make a form finding procedure, which is basically which actually only, so it's a hydrostatic shell, you could say, that's mainly is about only having the load is based on the soil. pressure. And you can see this in, for instance, the Maidenhead railway bridge, where you see that the form of these arches are actually not really a catenary, which you would sort of imagine if it was only gravity, but you can see kind of this on near the edges of this arch, how it's actually start to have this added curvature. So we looked a bit on also this French engineer who built masonry bridges in the 20th century beginning. And then we formulated so these are the membrane, this is the equations from membrane theory, basically. So what we have is we only have a load. The P is the load in the normal direction, and the P with which is 0 is basically we have no load in the tangent plane of the and then we apply this in the form finding procedure. So if you found anything of this interesting, sorry if I have extended the time here, but you can always look at these videos on my Vimeo, or as Allan said, read the my licentiate thesis if you want to know more, or check our homepage. So thank you so much for listening, and yeah.
Thanks, Emil. Absolutely brilliant. Really good. I'm